So welcome to this session. I'm really excited to be joining Codecamp again, this fantastic community. As I said, it will be my third time. This time taking it sort of from that initial presentation that I did 3 years ago around, you might have seen it around bees and reactive architecture, taking that into sort of the event-driven world and then taking that into the cloud native world. So I'm going to be talking about sort of how we can get to grips with what cloud native really means in terms of the architectural approaches, the technologies, the products, the tools that we can use to really architect and build cloud native applications and what this really means. And in order to do that, I'm going to be delving into the world of biology again. So a brief introduction to me for those who haven't met me. I'm actually a biology graduate. So I didn't necessarily take the most, say, usual route into technology. I studied primarily fish, as you can see. I'm diving in this picture. So that doesn't always come into my technology career much. I switched over to technology when I graduated, when I joined IBM as a software engineer. And now I'm a developer advocate, sort of specializing in Java, Reactive, the JVM ecosystem, and cloud technologies. But I like to be able to sort of utilize the biology knowledge that I have and that sort of understanding of the natural world to be able to link it via analogies to software methodologies, topics, technologies, to be able to hopefully simplify those down and really cement them in terms of how they can, why they all come together, how they work, and why they might be useful to your own applications. So in this session here, in previous sessions, I've compared, say, bees with reactive. In this session, I'm going to be looking at the anatomy of the body. So when I say anatomy, what do I mean by that? I've got a very handy definition here from Google. So when I'm talking about anatomy, what I really mean is this sort of branch of science that essentially is concerned with sort of bodily structure, so the contents of our body, how the contents of our body work together, and sort of how the inner workings of us sort of, I guess, just work in general, and why they've evolved the way they have. So in this presentation, I'm going to be breaking down cloud native using this analogy of anatomy. So why are we even talking about sort of cloud? Just to give you a brief introduction to this, you've probably covered a lot of this yesterday. So this evolution to cloud has been a gradual thing. So the first thing that sort of evolved was this underlying infrastructure that we're using. So this underlying infrastructure of, we used to have sort of single cores, but now we're able to take advantage of multiple threading, multiple cores. We used to have primarily on-premise servers. We're now able to take advantage of cloud infrastructure in terms of cloud servers, external cloud services, cloud provider platforms. We're able to take advantage of things that didn't exist before, like containerization, virtualization. We're able to naturally distribute our applications. So we're able to utilize this evolution of modern infrastructure, and that led to the evolution of our applications. So our applications developed from what used to be, primarily on-premise, primarily monolithic, quite large, sort of more clunky style applications. And we evolved our applications because we were able to utilize that underlying modern infrastructure. So we're able to, break it up into more microservice style architectures, break up that monolith into smaller pieces so that we could easily debug, deploy, and run out, say, new versions of a particular aspect of our application without having to bring the entire thing down, or just a single failure bringing our entire application down. So this evolution of our applications also sort of drove us towards this more cloud native, I guess, style of application development. So we had the evolution of infrastructure, the evolution of our application, and that leads to this. For those of you who have seen Toy Story, you'll know this. Ooh, the cloud. So what gets us so excited about the cloud? Why are we so sort of energized and looking forward to developing for the cloud? Well, the first thing we need to do is take a look at what the cloud actually offers. So these, in my opinion, are some of the key aspects of what the cloud really offers. So we've got things like cost. So if you think about it, when you're utilizing, say, a cloud provider, whether that's Google, IBM, Amazon, any of the large cloud providers. What they're able to do is they're able to work on sort of a larger scale. So you're able to basically cut costs because they're able to run the same servers and run huge data centers, and they're able to therefore do it at scale. So you've got cost reduction because they're able to do it much more efficiently than if you were running a single individual server for each individual business on premise. And so because those cloud providers are able to do it much more cost effectively, they're able to pass those cost savings down onto the people, onto the businesses and organizations using their cloud infrastructure. So there's a cost saving, which is fantastic. We've also got things like scalability. So unlike, say, on a more traditional on-premise style sort of application architecture and infrastructure, where it might take ages to be able to scale up anything within your application, scale up the infrastructure you need for it, for example, scale up the resources being allocated to that particular application or particular part of the application. In cloud, it's much, much easier to scale because they've got that underlying infrastructure, those resources readily available. So, as long as you've got the licensing and the costings in terms of the contract you have with that cloud provider, you should be able to rapidly and really efficiently scale up or scale down your application to be cost effective, as we just mentioned, but also to be able to deal with fluctuating loads to your application. So that scalability is really important. There's also speed. So being able to, as I said, rapidly get those resources up and running is a fantastic quality that the cloud offers. Resiliency is another one. So being able to say, if one data center goes down, being able to switch perhaps the geo of the data center you're running your application on, or even just the server within the same data center, enables you to keep your application up and running, regardless of whether a particular server goes down or whether a particular geo is blocked, for example. So it enables increased resiliency for your application. You're more likely to have an application that's able to switch underlying resources, switch geos, switch data centers, and remain up and running for your customers, which is obviously extremely important. Then you've got flexibility. So flexibility in this case is all about, if I have to run, let's say for GDPR reasons, if I have to run my data center in a certain geography, fantastic, I can run it in that geography, and I might be able to split it among multiple data centers, even within the same country, never mind the same region. And so in this way, we're able to flexibly determine where we're hosting our applications. We're able to switch that fairly easily. So if I needed to switch it from Europe to Americas, I could easily do that. If I needed to switch cloud providers, that's also fairly easy, depending on obviously the services you're using. If you're using some of the technologies we're going to be talking about later in this presentation, so for example, sort of containerization, virtualization, you should be able to fairly easily switch between cloud providers. So again, that flexibility of not being locked in because that one provider is the person who's given you the on-premise server, for example. So that flexibility is really great for cost savings and for the other factors we've mentioned already. Innovation. So we're able to utilize the cutting edge technologies, the cutting edge tools and underlying infrastructure and resources available from these cloud providers. And this enables us to focus on the innovation within our applications and make best use of that underlying infrastructure. So this innovation is another thing that the cloud offers. And fashion. You might not think of, say, software engineering or software development as a particularly fashionable industry, but when you think about it, it kind of is. We follow fashions and trends. So when microservices became a fashion, a lot of us might not have been the right choice, but we followed that fashion. And as we go to a more cloud native sort of fashion or trend, a lot of people are interested in this. And the fact that we're able to offer this to almost all organizations means that, the underlying infrastructure, the innovation that we're offering through these platforms can be accessed by everyone, and everyone is able to keep up with those trends and that innovation and that fashion. So this is what cloud platforms and the cloud in general offers to applications, and the reason it's so exciting going forward in our application evolution. So now that we know what the cloud offers, and we know we want to head towards that direction of sort of being cloud native in our application development, what does it mean to be cloud native? So I had a look at sort of various different vendor definitions, and actually the best definition that I found was one by the CNCF, which is sort of, as the name suggests, they are experts in being cloud native. So here is their definition of what it means to be cloud native. So cloud native is all about empowering organizations to build and run scalable applications in modern dynamic environments, whether that's public, private, or hybrid clouds. And you can utilize technologies like containers, service meshes, microservices, and immutable infrastructure, declarative APIs to exemplify this approach. Now, this is the reason I really liked this definition. It doesn't say you must use all of these technologies. It's just saying you can use these technologies. They help to exemplify the cloud native approach, but you don't have to if you don't want to. It might not be the right technique or methodology to use for your application. So that's why I particularly liked this definition. And the fact that they mention, these techniques, this cloud native methodology is all about enabling loosely coupled systems. Again, there's no mention of small, as you might get with the definition of microservices. It's just a loosely coupled system, whatever size you need, that are resilient, manageable, and observable. Again, key factors, but importantly, they're technology agnostic. So it doesn't matter what stack you're using. It doesn't matter what architecture you're using. It's just about being able to provide loosely coupled systems that are resilient, manageable, and observable, that are able to combine with, say, the robust automation that is offered within the cloud infrastructure to be able to make high impact changes frequently. As you've seen, as more applications have gone to, say, a more monolithic style or more cloud native style, they're able to, say, produce new versions, new GAs much more frequently, and thus offer, say, security fixes, bug fixes, and new features on a much more regular basis to their customers and their consumers. And to do that with minimal toil, so the minimal amount of disruption. To me, that is what cloud native is all about. So now that we've taken a look at why we want to move to cloud native and what being cloud native really means, let's take a look at what we need to consider to become cloud native. So what do we need to be thinking about? In my opinion, the first thing you need to be thinking about is, what are you trying to create when it comes to creating your cloud native application? There is a huge difference if I'm, say, playing God right now and I'm saying, right, I'm going to create some kind of animal thing. If there's a huge difference between me creating a very simplistic, say, sponge, or a very simplistic, say, bacterial cell, versus creating a more complicated animal, say like a worm, for example, and then going even further up to, say, cats, dogs, and then even further up to humans, chimps, dolphins, with a really complex system to deal with. So when you're thinking about what you need to do to become cloud native, it's really important that you sort of take a step back and consider, what am I creating in the first place? Is my app highly complex? Is it going to take a lot of different components and parts, or is it fairly simplistic? Is it, going to be fairly easy to be able to deploy and move to cloud native? So it's important that you consider the complexity within your application, because that's going to affect the choices you make in terms of the architecture, the technologies, and the tools that you use. So in terms of architecture, that's probably the next thing I'm going to be considering, because this is going to dictate sort of the technologies, for example, or the specific tools that you're going to be using. So when it comes to application architecture in cloud native, as has already been discussed in sort of yesterday's sessions, cloud native does not necessarily always mean you have to use microservices. It is about selecting the right application architecture for your application. Arguably, any of the microservices I have, any of the application architectures I have up on the screen here could be written in a way that is cloud native. The technologies and the tools that you'll use often are similar depending on what you're using. So we've got monoliths, macroservices, microservices, and functions. So we've gone from, say, sort of less coarser grained to more finer grained on the right-hand side. So functions are extremely cloud native, arguably because they just wouldn't work on an on-premise system. Most of the time when you're using functions, you're being charged per usage of the functions you've created, which just wouldn't really make much sense to do that on premise, because you're already paying for the underlying infrastructure and hardware. So it's really cloud native. Microservices are sort of where our industry has pegged cloud native. It's used in many of the vendor definitions, and it is a great sort of architecture to use if you're going cloud native, but isn't necessarily best for everyone. And that's because you can end up with sort of this idea of a distributed monolith where you've got all the downsides of a true monolith. You've got, tight coupling, and you're not able to loosely couple your systems to sort of separate them out. But you've also got the nature of distributed and lots and lots and lots of services to have to look after, manage, and you haven't really got the advantages of either. So that's the reason why sort of people are moving away from microservices. Macroservices are one way that the industry is moving towards. It's essentially just, imagine you maybe were looking at microservice architecture, but perhaps some of the individual microservices were quite tightly coupled together. Well, you could make that a macroservice instead. So slightly bigger than a microservice, but smaller than a monolith. So it's sort of an in-between there. And then you've got monoliths. So if we have a look at sort of how do you pick the best architecture type for your application, I would suggest using something like this. So this here is a slider scale. So the reason I've made it a slider is because very rarely does an application fit precisely in one category. Like, oh yes, my application is perfectly designed for microservices, fantastic. So in this case, it's a slider because it's a continuous sort of, there is no group necessarily like grouping. You could be sort of on this continuous slider between the different types. So on here, I put some of the key architectural characteristics you need to bear in mind to help you select the best type of architecture for your application when you're moving to cloud native. So based on, how often you deliver, what your operational complexity is, how your organization is organized, whether your network design, your modularity. So these are key aspects that you need to be considering and sort of mapping your own application onto this sliding scale, whether you're far to the left with monoliths, far to the right with functions, or somewhere in the middle, and then looking at where the majority of those different characteristics fall for your own application will probably give you a good indication of what type of architecture will work best for your application. And this is important because obviously it determines sort of how you go forward with the next steps in that cloud native journey. So please feel free to utilize this slide if you are thinking about moving to cloud native to map out where your application would be and select the best architecture type for you. So now that we've looked at sort of what architecture style are we going to be using, we now need to look at the different ways in which we can make our application cloud native. So one of which is, I mentioned earlier, this concept of containerization. And this is where I'm going to start sort of linking it into the anatomy and how we've already done a lot of this in our own evolution. So if you take a look at containerization within the body, so regardless of whether you've got macroservices, functions, or microservices, in the body, everything is contained. So let's say you're looking at a macroservice. You might think of a macroservice like an organ. But actually, if you were to delve into that organ, say the heart, is made up of lots of little cells. That might be the microservice style architecture. And those cells are heart cells. So it doesn't matter how you look at it. The heart itself is a container. And each of those cells is also a container. Everything within the body is contained. And that's really, really important because it allows us to create specialized cells, for example. So cells that are specifically for the heart that help pump, cells that are specifically for our skin that help protect us. So it enables us to specialize them and ensure they're in the right place within our body. And it also enables us these key factors like the ability to easily move them. Maybe they're not in the right place. Maybe they need to move somewhere else. We can easily move them because they're in that container. They're in that cell wall. We're also easily able to replicate them. So let's say I've been doing some weights at the gym and I need some more muscle cells. Well, I can easily replicate it because I'm just replicating the same cell. It's containerized. I can just spin up a new cell for that muscle to add to that muscle content to deal with that increase in load to my muscle. And I can also easily replace and fix them. So because they're containerized, we don't have to go looking for all the bits and pieces within it. We can literally just kill that cell and replace it with another one. So containerization is really important within the body, and it's equally important within our cloud native applications. So moving to this more distributed style of architecture, which sort of comes with the territory of being cloud native, means that we also need these same factors. We need to be able to easily move the resources within our application. We need to be easily able to replicate the resources or the different aspects of our application, and easily able to replace and fix it if things were to go wrong. And this is where sort of cloud native technologies like Docker, for example, come in really, really handy. So if we compare perhaps how we maybe used to do it with, say, VMs, so we've got VMs on the left-hand side here and containers on the right-hand side of the diagram. And you can see here that actually, we're able to massively reduce what we're containing within that container so that we can be as efficient as possible. And we're utilizing the underlying infrastructure. So instead of having to provide a guest OS in each of our VMs for each instance of our application, for example, instead we're able to utilize the underlying operating system and this container engine that's shared across most cloud platforms. So now we're able to create a container that's very lightweight, very easy to move and replicate, because almost all of the cloud providers use the same or enable the same underlying container engine, so that we're able to move that application wherever we need it to be, regardless of cloud platform provider, and we're able to replicate them really easily. They're very memory efficient. And so it's a really fantastic way of us being able to mimic the behavior of cells within our body in our cloud native applications. So this is a really fantastic sort of methodology to use, is using containers, and we can use tools like Docker to be able to do this. So now that we've containerized the different aspects of our application, what about, deploying them, scaling them, managing them? They still need to be sort of managed in this way. So let's take a look at the body. So the body is fantastic at being able to rapidly deploy new cells, scaling them depending on load to the system, and being able to manage them themselves. So we have this adaptability in the human body to adjust to factors or forces operating on us. So if we need muscle, for example, we just, our body is able to recognize that there's been increased load on our muscle, and then it's able to essentially send out signals to say, right, we need some more muscle cells to deal with this increased load. We need to create some more muscle. And that's how we're able to rapidly and sort of efficiently sort of deal with that load by increasing our muscle cells. And we're also able to do it with, say, cuts. So if we have a failure within our system, so in this case, we've got a failure on our skin because we've got an opening where there shouldn't be, our body is able to rapidly deploy platelets and red blood cells to form a scab to stop that becoming infected. So imagine if your cut is the equivalent in technology of a failure within the system. Now, if we didn't close that cut and it got infected, that small failure that looks like nothing could become potentially catastrophic and could cause our bodies to shut down and fail because of that infection. So that small failure could cause a system shutdown, essentially. It's the same thing in technology where, a small failure we should be able to reassign resources to be able to deal with that failure, however it needs to be dealt with, to be able to make sure our entire application doesn't come down. It's also clear in the body where we have, say, infections, like I was mentioning. If there's an infection in the body is able to utilize sort of antibodies to say, well, that doesn't belong in my body. And the body is able to send out some of our immune system cells to be able to tackle that sort of foreign body within our body. And what that means is that infection doesn't spread, and that single point of failure doesn't cause the entire system to break down. So our body has this fantastic way of being able to rapidly and elastically deploy, scale, and manage the different containers within our body, the different parts of our body. And we need to be able to do the same thing in cloud applications. And we can do that utilizing tools like Kubernetes, for example. So Kubernetes allow us to sort of automate this deployment and scaling and management of the various different containers that make up our application. Containers are often known as, say, K8s, if you know them by that name, and Kubernetes is also known as K8s, and it's an open source system for automating that deployment, scaling, and management. So this sort of links into some of the reactive concepts, which are also fantastic for cloud native applications, like elasticity, being able to deal with that fluctuating load to your application and not allowing a single point of failure to cause an entire application shutdown and to cause your application to become unresponsive. It enables us to keep our applications responsive and to make best use of the underlying infrastructure within our cloud native systems, especially when we've got such distributed nature of our applications. Okay, so we've looked at how we can deploy and scale and manage them. What about how they communicate? So communication is obviously vitally important in order for us to keep our application up and running, and it's the same thing in the body. So in the body is able to signal each component of the body, so each cell in this case, is able to signal to other parts of the body through various different mechanisms. So one of that is biosignaling, and that might be through hormones, for example, chemical signals, but we're also able to do it through electrical signals as well in our nerve system. So if something were to go wrong, for example, let's say a cell gets infected with something it shouldn't be there, that cell is able to send out a signal to the rest of the body, letting them know, I've been infected, someone come help me. And so we're able to essentially fix that as soon as it goes wrong. Nerves, for example, send out electrical signals to control different elements of the body, and hormones also do a similar thing, which is how we know when we're thirsty, for example, or hungry. And so this communication tends to be either a message-driven or event-driven within the body. So if it's event-driven, there might be, say, I touch a hot stove or a hot pan, and my body then sends electrical signals up to my brain to say, hot pan, let it go. And when I'm able to let it go through that rapid asynchronous communication. And that really enables, really fast, responsive actions to be taken, because it's really important that I drop that pan as soon as I can in order for my body to not be harmed any further, and to potentially cause a failure in the fact that I can't use my hand anymore because it's burnt. So communication within the body is really rapid, really asynchronous, and it's often message-driven or event-driven, either in the form of that electrical signal or a chemical. And it's important that we have the same responsiveness and the same asynchronicity within our cloud native app as well. So here you can see sort of an example of, say, a message-driven form of communication. We've got different services, so a customer order UI, taxi car service, taxi fleet service here, all corresponding via that central asynchronous message-driven system. And this allows us to not block parts of our application waiting for a response, for example, from another part. We're able to continue as normal, just like the body is, but we know that we've sent that signal out and that we will get a response at some point. So being really asynchronous allows us to remain responsive and as reactive to events that are continuing to happen as possible. So utilizing event-driven systems or message-driven systems can really help with that. And tools like MQ or Kafka can be really useful. Kafka is another open source tool that we could utilize for this purpose that really allows us to place that asynchronicity and decouple the aspects of our application through this asynchronous communication. So here we can mimic what the body does. We can mimic this type of communication to allow us to remain responsive in this distributed cloud native sort of environment. So what about the next step? So the next step I would say is sort of looking at, okay, we've looked at communication, we've looked at deployment and management of all of these different aspects of our application. What about where we're storing the data for these various different aspects of our application and that communication about, a lot of the time, about the data that we're using or the state of the different aspects of our application? Well, data storage within the body. When I say that, you might immediately think of the brain, because obviously it is a large store of data within our body. And it is a very useful store of data. And it's often where a lot of our cells will go to when we're referring to anything. So for example, to be able to throw a ball, I go back to my memory and I say, right, how did I learn to throw a ball? Oh yeah, I need to do this, this, and this, move my arm in a certain way and I can throw a ball. It's not that my arms remembered how to throw the ball, it just refers to my brain for that. However, what's clever in the body is that not all cells rely on the brain for that data storage. Essentially the same as saying relying on an external source for that state. Some of our cells are able to keep state within them, keep some form of data or memory within them. And that's really important within the body to enable really fast, rapid responses. So quite relevant to now, this links to our immunity and actually is the reason vaccines work, kind of related to our current pandemic. So the reasons vaccines work is that we're able to create memory cells. So by infecting us with a fake version or a dead version of that particular virus or disease or infection, we're able to test our immune system. So our immune system has to then recognize this new foreign body we've not seen before. Once we've gone through the usual process of, oh, yeah, we finally recognize that it's a foreign body, it usually takes a while because the brain has to figure it out. Once we've recognized it for the first time, our body makes something called a memory B cell. Memory B cells are literally designed specifically for the purpose of remembering what we've previously been infected with, whether that's a cold or a flu or something worse. And that means that when our memory cells are able to see that foreign body in our system, instead of having to go to the brain and think, okay, is this a foreign system? Is it not? Have we seen it before? Should I get rid of it? Instead of having to go through that entire process, the memory B cell automatically kicks in and says, that's a foreign body, we need to get rid of it. And so this allows us to have a much more rapid response to potential infections in our body. And this is sort of similar to the stateless versus stateful sort of argument that you might have in terms of how best to store your data within your application, because the brain is sort of, I guess the cells that utilize the brain as that storage are kind of stateless because they don't hold state within them, whereas the cells, the memory B cells that do hold that sort of memory of what we were previously infected with are kind of stateful because they hold their own state. They don't rely on an external source. So in your own application architecture, it's important that you think about, okay, am I using an external data source? Am I making more stateless microservices or stateless components of my application? Or do I need to hold state within my application? Do I need to remember what last happened with my own application, have this in-memory data? So it's important that you consider the different aspects of your application. And it might be the case that you use a mixture of both, but there's not necessarily one approach that fits all. It's just a case of, spending time thinking about what would be best for your own application. Is it stateless? Is it stateful? And what, if it's stateless, what kind of data storage externally are you relying on? Is that asynchronous? Is it some kind of database? Are you using message driven or event driven? And that's really important to consider. And it kind of links in with that communication that we talked about previously. So in the body, we utilize both. It's completely up to you within your own application, what type you use, but it depends on sort of the characteristics of the individual services and the different components of your application. Okay, so we've looked at sort of communication, we've looked at data, we've looked at management of the different aspects within our application, within our body. What about when things go wrong? Now, in software development, we always have to be prepared for things going wrong. That might be something we've done wrong accidentally, saying a piece of logic within our code is broken, or perhaps a resource has gone down that we weren't expecting and we don't have failover behavior, or it might be out of our control. A data center might have gone down, an external service we're relying on might have gotten broken. So it's important that we think about what behavior our application has got in place for when things do go wrong, and how our application can deal with that to prevent us from having an unresponsive application and to get it up and running again as quickly and efficiently as possible. In the body, we already have sort of this in process. So there's something called homeostasis. Homeo meaning sort of relating to us, and stasis meaning sort of the state of us. So we're looking at sort of homeostasis being this definition of looking at the state of sort of internal, physical, and chemical conditions maintained by living systems. So in this case, you can see that there's various different organs within our body that allow us to constantly monitor and look at the metrics of different aspects of our body. So for example, the hypothalamus in the brain allows us to regulate temperature and osmotic, so water pressure. Kidneys allow us to maintain water balance. Our blood is able to distribute heat effectively throughout the body. And we've also got things like the pancreas that regulates blood sugar. So our body is constantly being monitored and checked to make sure that everything's as it should be. And if it's not, we're able to put actions into place to prevent us from potentially causing a system shutdown, death at the worst, if these things go wrong. And so we're able to do things like control our body temperature through our blood distribution. We're able to cause ourselves to heat up by shivering if we get cold, for example. So by constantly measuring these sort of different metrics within the body that are vital for our survival, we're able to then monitor if they go wrong at any point constantly. And if they do, we're able to put actions into place to negate that and to stop it becoming a failure that continues and potentially causes a system shutdown. So this is kind of the equivalent of having a dashboard looking at all of the vital metrics in our applications and acting upon any sort of sign that there's potentially a situation that needs to be acted upon. So this is what we need to include in our cloud native applications. With distribution of our different components comes this responsibility to be able to monitor and check that they're all okay. Same as in homeostasis. We need to check that every aspect of our body is still working correctly and is still as it should be, that our temperature is at the right temperature, that our water levels are correct, that we don't need to drink more, we don't need to eat more, we've got enough sugar, all of the rest of it. It's an extremely complicated process in the body. And it can be, seen as complicated because of this distributed nature of cloud native applications rather than on-premise, where perhaps you could just take a look at all the logs automatically. So there are various different tools that can help with this in order for us to gain the same observability in our cloud native applications as we have in the body. It's all about having this observability of the different components. So we can use things like Prometheus. You might come across that before. It's, again, another open source system that enables monitoring and alerting. So it's essentially a toolkit you can utilize to enable that observability. So it scrapes metrics from, say, instrumented jobs, either directly or via, say, a gateway of some kind. And then it stores all of those scraped samples and runs rules over the data to gather sort of aggregate data and record sort of time series. And then it can create visualizations using things like Grafana or other API consumers to visualize that collected data, so you can see what's happening in real time in your application, and you can potentially act in a responsive way to potential failure points. We can also use things like Elasticsearch. So that enables sort of raw data flows into Elasticsearch from a variety of different sources, including logs, system metrics, and web applications. And then it's able to do the sort of data ingestion process where it parses the information and enriches it before it's indexed. And so once it's indexed, users can then run complex queries against their data, and they can create sort of summaries and, again, create powerful visualizations through tools like Kibana. And they can create sort of dashboards and manage that stack. So again, these can be some really useful tools to enable that visualization and that observability in our application to ensure everything's stayed working correctly. So I mentioned the fact that the human body is fairly complex, and that involves some important navigation techniques when it comes to managing, organizing, and controlling different parts of the body. So in the human body, we have this ability to utilize our central nervous system and our periphery nervous system. Central nervous system being sort of your brain and your spinal cord, and your periphery nervous system being all of the different nerves that span out all over your body that help control finger movement, hand movement, arm movement, and all the rest of it. So by utilizing these two points, especially the CNS, it enables us to have this sort of one point of entry where we know we can access everything else within the body. So our brain is able to use the central nervous system within it and within the spine to know, oh, if I just send a message to the spine will know to send that to my hand to wave it, for example. So we're able to navigate this hugely complex neural system by utilizing this centrality, this central point to go through. And we need to be able to sort of implement the same techniques in our cloud native applications to help navigate their complexity too. As I mentioned, as you move from on-premises to cloud native architecture and application infrastructure, you've got increased complexity that comes with it. But to enable sort of greater simplicity in terms of how your application is able to navigate this complexity, you can utilize things like proxies, for example, load balancers, gateways, and these enable you to provide a central point through which all requests can be sent, so that if the backend changes at all, it doesn't cause you to have to rewrite the entire logic within your application, for example, and you can deal with that potential failure point. And it also enables you to load balance across different instances of your application, so one isn't completely overloaded, and you're able to do that dynamically depending on how many users are accessing your system, how many instances you have up, where they're located, what resources are assigned to them. So it enables us to really simplify the complexity of this application. And we can use things like, they basically act as intermediaries in the communication between, say, clients and our servers, helping us to perform functions more efficiently. So we could utilize things like Kong Gateway, for example, is an API gateway tool. It enables sort of highly scalable, again, open source API gateway, and it's really optimized for microservices and distributed architectures, which is obviously important in our cloud native application, where most of the time we're using really distributed architecture types. This gateway also allows developers to sort of configure requests and responses on the fly, so it's really great to use. Or you could use tools like Nginx for load balancing. So we've taken a look at various different sort of technologies and tools and methodologies that we need to consider when we're creating our cloud native applications. We need to think about how we're designing it. What architecture type are we using? And that depends on how complex our application is, what functions it has, what characteristics it has. We've looked at, okay, regardless of that application architecture, we do need to use containerization. And that's to enable that easy replication, easy bug fixes, easily to, say, move if we need to at all. We then looked at, okay, if we're using containers, we need to be able to deploy, scale, and manage them effectively. We then looked at, okay, we also need to look at the communication between those different components, between those containers, and look at how we're communicating within our application logic, but also with our data storage and how we're storing that data. And then we also looked at, being able to keep that observability up, being able to monitor our application to make sure that in the case of something going wrong, we're able to act and negate that and stop a potential failure point. And we're able to sort of simplify that, all of that complexity, by adding in these central points for communication within our application between the client and our servers and our backend. But how do we actually go about achieving this? I've mentioned some of the tools that you could use, but obviously there's a huge plethora of tools that are out there, depending on, say, the language you're using to develop your application, the cloud platform you're using, because some cloud platforms will offer specific sort of cloud tools and technologies that you could be using. And it also depends on the sort of style and characteristics and needs of your application. So let's take a look at sort of how we can achieve this in a more agnostic manner. And sort of one of my favorite methodologies to follow for this is the 12-factor, or as I mentioned earlier, you can extend that to the 15-factor application methodology. The reason I really like this methodology is it actually links to a lot of what I've described in this presentation so far. So being able to sort of use dev prod parity. So when you're testing, being able to keep the testing environment, the staging environment, the development environment, and the prod environment as similar as possible. Being able to use sort of disposability, having one code base, having external configuration. And the reason I like this methodology for cloud native applications is because it is technology and platform agnostic. All of these characteristics can be used regardless of what stack you're using, what language, what cloud platform. So this is a fantastic way of developing an application that's ready for cloud native without necessarily prescribing technologies or methodologies or particular platforms. So definitely worth checking this out. I put a link to the 12-factor app website at the bottom of this slide if you'd like to take a look in closer detail. You could also look at things like the CNCF Cloud Native Trail Map. So I mentioned the CNCF earlier, that's the Cloud Native Computing Foundation, and they're the ones I took the definition of what Cloud Native was from. In this Cloud Native Trail Map, they offer sort of step-by-step instructions on how you can migrate your application to be cloud native through techniques like containerization, orchestration, like I mentioned. So again, this links really closely to the various aspects I mentioned in the presentation and why they're important in our applications and why our body uses them already. There's a reason our bodies are so efficient, and that's because we've had millennia to evolve it, and our bodies have evolved to be efficient in this manner and to utilize these techniques because they are efficient and they work and they enable us to sort of come back from potential failure points and not just shut down and die. So, there's a reason that we can use nature in this regard to sort of inspire our software architecture choices. And so, yeah, this is another sort of methodology or map that you can follow if you want to migrate to cloud native. Another field guide you could use is the IBM Garage methodology. So again, similarly, this takes you on step-by-step instructions on how to migrate to sort of being cloud native and modernizing your applications. So again, I put the link here if you'd like to check that out. if you want to get hands-on with a lot of the technologies that I've mentioned throughout this slide, like say Docker, Kubernetes, as well as other tools like proxies, for example, gateways, and other cloud native technologies like MicroProfile. So MicroProfile, for those of you who haven't heard of it, is an open source specification designed for sort of applications that are utilizing Jakarta or Java EE to enable them to become more cloud native. And we offer interactive cloud native online labs if you'd like to have a go with any of those technologies and get hands-on with them. So I put the link here to that lab. Feel free to go and check it out. The labs will be up for quite a long period of time. We don't plan to take them down anytime soon. And it can be a really fantastic way of getting hands-on with this technology. If you don't want to do it in an online environment, we also offer these Open Liberty guides, which is the same as the online labs. It's just these are designed for local development. So if you want to do it locally on a laptop, you can also utilize the same material in guide form from our Open Liberty website. Just for reference, Open Liberty is our open or web application server. So that's why it's on this site. So if I haven't given you enough links already, I've also got some other useful links that you can follow around sort of giving you an overview of cloud native, again, giving you a couple of other step-by-step guides on modernization and how to become cloud native. And then if you want to go into a deep dive on sort of a comparison between the analogies I've used, I've also done a video right at the bottom there of this slide. So hopefully these will be useful to you if you want to go off after this presentation and check this all out in greater detail. But I think I'm at time, so I will stop there. Thank you so much for listening. Hopefully I've shown you that sort of biology can be a really great inspiration for us considering the key aspects to make our applications more effective in such a distributed environment, utilizing that underlying infrastructure as effectively as possible. My name is Grace Jansen, and as I said, if you have any further questions that I don't get round to, please feel free to tweet me at Grace Jansen 27. Thanks very much.
We will do so. A big round of applause for Grace. Thank you very much. I very much enjoyed the parallel that you've been doing between the anatomy and the cloud native cloud migrations. It very much reminds me of how useful was for me, the brand sharing layers for understanding how to plan software architecture, not just buildings. Not that I'm planning any building architecture, of course.
It's basically the same thing. That's what
kind of the same thing.
We used to hear.
I mean, yeah, it's like how many buildings? 10. Okay, then multiply the estimates with 10. It's gonna be okay, right? Yeah. Looks like, I mean, speaking from the recent experiences, so cloud migration is a complicated thing because it involves a lot of strategic decisions, and you really need to have some, not some, but expertise and experience and guidance if you want to do this. It requires a lot of planning. From your experience or some recent experiences with clients, what do you, maybe encounter more oftenly as, approaches or we want to learn from?
Absolutely. So I think you mentioned a great point in that it is complex. It does involve a lot of strategic decisions. And that's why it's important not to just follow the fashion or the trend. I think it was mentioned yesterday, people jumped into the world of microservices because they were like, oh, Netflix have done really well with it or whatever. I'm going to try and do the same. I mean, most companies do not have the resources or the money or the expertise that perhaps Netflix had. Every organization is different. Every application is different. It's about taking the time to understand your specific business needs, the characteristics of your application, and applying that to the technologies and the tools that are available. I would say, I think we've progressed a long way since we started moving to cloud, and the open source community, I think, is a huge help in that because, they've created these open standards and tools that we can all utilize now instead of having to try and figure it out ourselves from scratch. So I would say my two pieces of advice would be take the time to understand your specific application needs. Don't just follow the trends. And the second thing is utilize the open source technology and community to really, follow these standard trends and utilize these open source tools as much as possible.
Right, and let's not forget that it's not just about the application and the technology that you're having in the in the organization. It's very much also very much about the culture and how
Absolutely.
people behave and understand technology.
Yeah. So I mean, if you saw my slider chart, I had a couple of characteristics on there that aren't relevant to your specific application. Things like your delivery frequency. Different organizations deliver at different times, and that's based on culture and how your organization does processes and how your organization is set up. These are all key factors that will also come into how you modernize your application, because your organization might not be set up in a way that's best for microservices, for example, even if your application is. So it's important to remember it's not just about the technical, it's also about the culture, the processes behind it. There's a whole other sort of infrastructure to think about when it comes to that.
Right, and I also liked I think that slide of yours with the slide with the sliders. There, I said it. Because indeed, if you have, for instance, a small team and maybe you're releasing twice a year and probably you're releasing everything together, there's no point in going for microservices.
Yeah, exactly. And it might make more sense for you to go for even a more monolithic approach, depending on the size of your application, or say macroservices. So that's why it's really interesting, depending on like all of those, you can add additional characteristics if you think of them to that slider list, but it's interesting to use it to see where your application falls.
I've got another question. Maybe it's a bit off topic, but still it's about cloud migration. So in the past 2 years, the last year, and it's continuing even, especially in the EU, the GDPR and data protection and everything kind of, exploded. Yeah. I mean, more and more states, Germany probably is in the pole position, is looking at the cloud, whatever that means, and even more cloud native, whatever that means, with suspicion because of the way data flows or not inside the EU.
Yep.
Speaking now of IBM, how is IBM prepared to handle that, if you have any?
So at IBM, we have we take a lot of pride in terms of having security of data, ownership of data. We have a huge emphasis on ensuring that the businesses and the enterprises and the companies who are creating these applications have the ownership over that data. We provide sort of ability to be able to specify a specific geo or location that your data needs to be in. So as you say, if, for example, we're working with governments in a certain country, often the data they're dealing with needs to be kept in country. So as best we can, we try and offer geos that fit with those specifications and those requirements. So being able to ensure that, that data is yours and that no one else is able to access that data, ensuring that we're supplying that data in the correct geographies, depending on those data centers and those requirements, and ensuring security of that data by utilizing some of our cloud sort of platform offerings.
Especially after the Schrems the second, if I can call it so, I've seen a lot of reactions and from clients inside the EU with respect to data leaving the EU. Because let's face it, I mean, the major or all the big technology and cloud providers are not in the EU. Am I right? Or should we say that IBM is, or Microsoft or Google or?
So I mean, I can't speak for the other cloud providers, but I can speak for IBM. I
can speak, no problem.
I mean, with IBM, although we are technically an American company, obviously we were founded there, we are a multi-global corporation. So we actually have data centers all over the world in the different regions. So we do have data centers in Europe and in England, for example, in different countries within Europe. So with the GDPR, for example, we do offer the ability to restrict your data to just being, so your application's just running in those European data centers. So that way you can restrict where your data is flowing, ensuring that it's within the same country or the same location or region. I don't know about the other clouds.
People are still struggling with it. I mean, everyone understands that the data centers are in Europe, not a problem. But does any data leave EU? Because you need to communicate, with the domain, whatever, firewall or domain load balancer, or which could be or not in the EU, and somehow data lives. And we struggled trying to explain clients that this is not an issue. But to be honest, I was not totally convinced. So I left the conversation somehow pending in the air, and asked the providers, and not all had like a German style type of answer, like starting A, B, C, D, right?
Yep. I think it really depends on how you've architected your application in terms of what external services you're relying on, for example, because as you say, that could be a potential leakage point. And B, it depends on how you've provisioned your underlying infrastructure. So for example, if you're using a more public cloud, you have the potential that provider might switch where that data is being hosted, whether that's still within Europe, but it might be in different data centers that you say. But if you're using, say, like a private cloud, for example, or like a cloud that's been provisioned, like resources that are provisioned just for you, it means that obviously you're the only one using that underlying infrastructure. You know exactly what data center it's going to be in, and that's not going to change. So I think it depends on, there is emphasis on, if you are using external service, you need to make sure that that connection is secure. You need to be understanding where that underlying service is being run from. Is it being run in the same infrastructure? Is it being run somewhere else? And then you need to also understand, the type of infrastructure you've got as part of that contract with that cloud provider. Is it provisioned specifically for you? Are you sharing it with someone else? Is it a hybrid with an on-prem? How are those two connecting? Are you using some sort of secure system to be able to communicate between those two? So there's various different factors you need to consider, some of which are process orientated, some of which are design decisions within your application.
You convinced me, so I got the confidence to carry on.
I'm glad I passed that on.
Exactly. Thank you so much.
All right. Yeah, thank you very much, Grace. But I think I have to correct you with one thing.
Yep.
I think this is your 4th Codecamp.
Is it really? No way.
You've attended 2 of them in person.
He's keeping track. Oh yeah, of course.
And then
in the same year.
This is the 2nd one online.
And I thought Dan is a cloud specialist, and he wanted to correct something on the...
Well, it's lovely to be back for the 4th time.
Looking forward to the 5th.
Exactly.
So now that we broke the trilogy, we can count, again from 1.
Absolutely. Just go back to the beginning, right?
Yeah.
Thank you so much for having me, guys. It's been wonderful to join you again.
Thank you.